need to do a range match on CO2 or H2O individually. You can't do both at the same time, because what we do is we change the CO2 concentration or the H2O concentration, and we monitor its behavior, and the algorithm doesn't let you do both at once. But it doesn't take that long. If you're interested in doing range matching and thinking about range matching, we do have a video that talks about how to do it, what to do, what to consider, and things to keep in mind that might be particularly helpful to you. We'll also talk about range matching a little bit more as we go through the course. So when we point match, we might still need to point match after we range match. And here are some times when you might want to point match even after you have a range match. You might want to point match when temperature changes more than 5 degrees C. It's back to our friend, the ideal gas law. You may want to match with low rates, low photosynthetic rates, so that you make sure that if there's any kind of change in CO2 or any kind of offset, that we know about that. And you also might want to point match if you have a large change in flow, just to make sure, again, that things are staying on target. If you're not using range matching, then we point match before the first measurement, when we start our day, when we have low rates, if there's a change in operating CO2 concentration, if there's a large change in flow, and every 30 minutes if none of that is true. Are there any questions about the hardware, how the hardware works, or range matching and how that works with the hardware? Okay. So, building on what we have already talked about, we have talked about how our gas exchange parameters are measured in terms of the electronics. We have talked about how the instrument is designed, and we have talked about how we can make sure that what we're measuring is what we think we're measuring in terms of working on minimizing diffusion and making sure that our response time is fast, and also matching our analyzers so that the number that we get is as close as possible to the right number. Once we have confidence in those things, then we can start saying, well, what if I don't want to look at just assimilation or just transpiration? There's other things I care about. What can I look at? We can look at things like stomatal conductance to CO2 and stomatal conductance to water. We can look at intercellular CO2 concentration. If we combine gas exchange and fluorescence, we can start to look at mesophyll conductance. The confidence that we have in the basic measurements means that we can then extend that measurement out. We can say, I measured this, now I can calculate that. All these parameters are calculated rather than measured. What's measured is assimilation and transpiration. So, measured parameters: incoming CO2, outgoing CO2, incoming water, outgoing water, air temperature, leaf temperature, atmospheric pressure, flow rate, photosynthetically active radiation. From these basic measured parameters, we can get assimilation rate, transpiration rate, stomatal conductance, intercellular CO2. Now, transpiration rate is in gray rather than in black because there are some assumptions that we make about transpiration rate that we have to keep in mind when we want to analyze our data. And we'll talk about that a little later. But transpiration rate is something that we do. We measure it in a chamber rather than in the natural environment, and that does affect the transpiration rate. One way that we might be able to think about the relationship between conductance, assimilation, transpiration is using V equals IR. what we can do is we can think about the relationship between resistances. So every time a molecule of CO2 moves into the leaf or a molecule of H2O moves out of the leaf, there are forces that create resistance. So for example, there is the boundary layer, and that molecule of CO2 or H2O has to move through the boundary layer to get to the stomates. Then there's stomatal conductance, how quickly and the rate at which the molecules of CO2 or H2O can get into the stomate. Then there is the mesophyll conductance, which is the rate at which the CO2 gets into the mesophyll so that we can actually do photochemistry, the carbon reactions of photochemistry. So each of these points along the pathway has something that might slow it down. There might be a roadblock. There's something in the way. And so what we can do is we can measure and calculate the resistance, which tells us, well, if this is the CO2 concentration here and the resistance is this, then what is the CO2 concentration there? You know, how much lower is the CO2 concentration in the leaf if I keep in mind that not all of it was able to make it into the leaf. So we look at the way that we know CO2 and H2O react and interact with each other. For example, CO2 diffuses out between 1.3 and 1.6 times as fast as H2O diffuses. CO2 diffuses in 1.3 to 1.6 times slower than H2O diffuses out. So what that means is that the leaf is going to lose water every time it takes up CO2. This might be a calculation it's willing to make. I mean, it needs the carbon. But if you don't have that there, then you have to keep in mind, okay, well, if I have to take up that CO2, but I don't want to lose all my water. So then the plant starts working on that kind of calculation as what's worth it in terms of opening the stomates and taking up CO2 but losing water. So if we think about the relationships and the resistances, then we can then look at it and say, well, if I can measure E and I can measure A, I can measure water concentration in and out. I can then measure leaf temperature. I can look up or assume internal water concentration, and then I can solve for CI, and then I can solve for stomatal conductance and CO2. Stomatal conductance to water and stomatal conductance to CO2. This allows me to get not only E and A, but also GSW, GSC, CI. The challenge is that if there's any problem anywhere in the calculation, then our measurements are not going to be correct. So we start with E and A, and then we do a few calculations and we get GSW, and we do more and we get CI. So CI is what we refer to as a highly calculated variable. It's a variable that's calculated from other variables. If anything is wrong anywhere in that calculation path, then there's an issue. And so then we have to keep that in mind. Specifically, the thing that tends to affect stomatal conductance and thus CI is boundary layer conditions. Even in a leaf that is normally, the air around it might be very dry. It might be in the desert, and the air around it might be, to our perception, 20 to 30% RH. So dry. Around the leaf, though, there's always a layer of highly humidified, saturated air. And that allows us to make sure that the leaf allows the leaf to make sure that it's kind of safe. It's a little coat for it. But that boundary layer of saturated air is very difficult for us to measure. because of the amount of air, the water preventing the CO2 from getting there. So what we do in the chamber is we basically strip away the boundary layer. We take it away with our mixing fan. And what that does is allows us to say, okay, well, it's now easier to measure, but we've taken away our leaf's protective coat. And our leaf might not like it that we have taken away its protective coat. So if you have a coat because it's cold and someone takes it away, what happens? You might start shivering, you kind of close in on yourself, you try to make yourself smaller. The leaf kind of does the same thing. The stomates close so that the leaf can be protected. We don't want the stomates to close. If the stomates close, then we don't have any gas exchange, or we don't have as much gas exchange. Then our measurement doesn't work well. So what we have to do is give back that extra air, that extra humidified air. So it ends up looking a little bit like this. In a chamber with not very much humidity, the stomates are closed, there is no gas exchange, there is nothing for us to measure. If we give it a little bit of extra humidity, then the stomates open and there's a little bit more gas exchange because we've made it more hospitable. We've made it nicer for the leaf. And it says, okay, there's enough humidity here. I can go ahead, I can do this. Then we add a little bit more water. And it says, oh, wow, there's plenty of water here. I can keep my stomates open as much as I would have had them open if the boundary layer was completely there, had not been removed. But what we don't want to do is get into a situation here in the lower right-hand corner. What happens there is that there's so much water that there's no difference between the inside of the leaf and the outside of the leaf, which means there will be no exchange. And if there's no exchange, there's nothing for us to measure. The other thing that happens is that then we have the possibility of so much water being in the air that there might be some kind of condensation in the air. And then now it is raining inside of our, we do not want it to rain inside of our instrument. So we say, okay, let's avoid this situation here where it's so dry that the stomates will not open. And let's avoid this situation where it is so wet that there is no difference between the inside leaf and the outside leaf. And also we might have a problem with our instrument. What this means for making measurements is target boundary layer conditions. Even if it's 30% relative humidity to your perception, remember that it's 50 to 70% relative humidity in the boundary layer. But if you can, controlling on VPD is even better than controlling on RH. RH is a human measurement. It's designed for us to think about humidity and things like that. The plant actually thinks in terms of saturation vapor pressure. And so if you use a constant VPD of 1 to 1.5 kPa in the LI 6800, that's going to mimic boundary layer conditions pretty well. The other thing that this means is going back to that transpiration term I mentioned that I had grayed out. So if we change the boundary layer, then we change the transpiration gradient. If we change the transpiration gradient, then interpreting water use efficiency, which is a very common metric, is not as correct because we artificially altered that transpiration gradient. You'll often see people refer to instantaneous water use efficiency, and that is just A over E. And this works if you were, say, looking at an eddy covariance system or something like that, when you're not altering the conditions. When we're in a chamber and we're altering the conditions with the mixing fan to strip the boundary layer, and then we're giving it back, but perhaps not to the same amount, then we should consider using intrinsic water use efficiency, which is